Okay, we're going to have a look at the d orbital complex ion lab. And this is analysis of the color of two different nickel complexes. Okay, so I'm going to note here up at the top about ligand field strength. That's just what you had from your notes already. The two nickel complexes I'm going to look at are shown in the picture there, but they're the nickel complex ion that has 6 waters, and then when we add the ammonia to it, we have the nickel complex ion that has 6 ammonia ligands. Okay, so the color goes from from green to blue. All right, we're going to look at the Y. All right, it's kind of important that you get the order of the Y correctly. Okay, so there's the two respective ions. Alright, so here we'll balance that equation just for completeness. But now we're going to draw sort of that partial Aufbau diagram for the nickel water complex. Alright, so I'm going to split the d orbitals. Alright, I'm going to populate the low set and the high set of electrons. Alright, nickel 2 plus in this case. So that it would lose the 4s electrons. It would have the 2 remaining, it would have 8 remaining d electrons. So I'm just going to fill those in. Alright, I'm going to show the gap that's what we label as delta octahedral. And for right now, it's just a random spacing. Alright, this would be the electron that would move up and down. Okay, or sorry, the transition from low spin to low to high yields that green color. Okay, so now why is it that we eventually get the blue color? Well, first let's have a look at the color wheel. Oh, this will take you back to your childhood a little bit. Let's actually swap this one out though for maybe something a little bit more usable. Okay, so we've got the color wheel here, and let's try to match up observed and absorbed. So the first color that we observe is a green color. Alright, so we'll trace that back through. Alright, which means that we used a red photon for that, so that's the green solution. Alright, we're going to call this observation 1, or OBS 1. Alright, now what's this? And so this required a red photon, as I just said. Okay, and a red photon is relatively low in energy, okay, compared to the next photon. Alright, so the second observation is we have the blue solution. Okay, so how do we get a blue solution? Alright, blue solution means that a yellow photon was absorbed, and we're going to call this observation 2, or OBS 2. Okay, so a yellow photon is relatively higher in energy than the red photon. Okay, so why is it that the solution needed the higher energy photon? Alright, so we're going to draw our partial d orbitals. Our partial Aufbau diagram again. I'm also actually just going to go back and I'm going to label the two complexes. So, on the left-hand side, I was working with the water complex, and on the right side, I'm going to work with the ammonia complex. Okay, but ammonia is a stronger field ligand. Now, as a result, what happens is the d orbitals split more than they did in the presence of the water ligand. So I've done my best to illustrate the relative spacing being larger here. So the relative value of delta octahedral would be larger, the gap is bigger. Okay, meaning that it's going to take a little more energy for the electron in the lower set to move up to the higher set. Okay, hence where the yellow photon comes in, thus the change in color. Why did the orbitals split though even further? Okay, so delta octahedral is larger. That's what actually results in the higher energy photon. Why was delta octahedral larger though? ammonia, NH3, is a stronger field ligand, so it's higher up that series of ligand field strength that you guys have to know. Okay, and as it's a stronger field ligand, what it does is it causes the d orbitals to split even more. Alright, and the larger split requires a higher energy photon, which results in a different color that we observe. Okay, so in this example, we went from needing a red photon to produce a green solution to needing a yellow photon to produce a blue solution because the ligands changed and we got a larger gap between the lower d orbitals and the higher d orbitals, meaning that we needed more energy to complete the transition. I hope this helps.